Okay, welcome to the third week of classes. In the preamble, before the 10 minutes before class started, I hope you enjoyed the conclusion to the Look Around You Calcium segment. You know, the conclusion there was don't give calcium to gypsies for some reason. Oh, that program gets me every time. That's pretty funny. You'll also notice when they wrote calcium on the board right at the end there, they even spelled calcium wrong on purpose, I bet. And to follow up that little clip, because I didn't fill the full 10 minutes, what you just witnessed there was the Queen song, Show Must Go On, arguably one of the best rock bands of all time. And Freddie Mercury was the lead singer in Queen. He was a pretty interesting guy. He's actually born in, well, not the UK. I think Tanzania, I believe he was born in, and but he lived and grew up somewhere in the UK. And an interesting physics-related note to Queen, one of the lead guitarists, the guy with the crazy hair that kind of looks like Sir Isaac Newton, his name's Brian May. He actually has a PhD in astrophysics, which is kind of interesting. So I guess there do exist some physicists with a creative side. There aren't very many of us, but I guess Brian May is evidence that there exists at least one of them. Okay, I guess without further ado, let us jump right into what we are going to do for today's lecture. So I hope everyone kind of got through the weekend okay. It was a long weekend here in Canada, so I don't know where you're tuning in from. If it's outside of Canada, you would not have necessarily realized we had a long weekend. But Monday was Victoria Day, so it was a stat holiday, so we didn't have lecture yesterday. And on Friday evening, you had an assignment due, and then Sunday evening, you had the intro assignment due. So it's very important that if you did struggle with some of the questions on either of those assignments, you review the solutions, and the solutions to both of those assignments are posted and readily available for you guys to review. This course, as with any other course, especially in the sciences, future topics build on previous topics. So if there's something from the beginning of the course that you're still tripping up on, it's going to compound. And as we move forward in the class, if there's still something from the beginning you don't get, you know, the future things we present are still going to be problematic. And a common misconception in this class is that error propagation is, you know, not that important. You know, like if you just don't do it and you don't understand it, you might just get a few marks off on your labs, but no big deal. But in reality, you know, most of you in this class identified as being pre-med or in the forensic program, both of which are very empirical fields of study. You know, when you're being a doctor, like those you know, real life statistics are quite important, you know, but before you launch into a surgery or try a certain type of drug treatment, it's really important you understand the uncertainty and the risks and the error involved in certain types of new experimental procedures or drugs. And same thing with forensics. I mean, if you're going into the forensic sciences, you're going to be helping the police do investigations. And when you come up with, you know, evidence that you report to the police, you have to, you know, in some sense, you've got to report how confident you are in your findings. So, you know, you can't say like, oh, I'm 100% sure it was, you know, this piece of evidence. There's going to be some sort of uncertainty there. So, you know, this class aside, there is a reason why we're trying to teach you uncertainty, and we're trying to frame it in the context of a physics course, because you are doing labs, virtual labs, but still labs nonetheless. But these are skills we're trying to teach you moving forward. So, you know, they will be a reoccurring theme throughout the course and in your careers and in whatever majors you're choosing to go into. So please try to make an honest effort, you know, if for no other reason than for the upcoming midterm. That's why we actually have midterms. It's to force students to actually sit down and do their work. But you know, you shouldn't be in a class for the class. You should be in the class to learn and to train you for whatever future job and career you're trying to train for. So you know, your mark in this class is inconsequential. It really honestly is. So you should really be focusing on your learning and your understanding, because that's what you're going to carry with you for the rest of your life. Okay, we'll talk more about the midterm tomorrow. I think we're not quite we got stuff to do today, so we're not quite there yet today. I will remind you though that I have a survey. A link to the survey was on the announcement I posted on the weekend. It's a time zone survey. The midterm is scheduled to be 8 a.m. to 10 a.m. on Saturday, this upcoming Saturday, May 23rd. And there have been a few students that have expressed an issue with the time, specifically for students to the west of Toronto. East of Toronto is not a problem because, time moves forward as you go east. So, 8 a.m. Toronto time would be, 6 hours later in the afternoon in Europe, and even 12 hours later over in Asia, or 13 hours later over in Asia. So those people are not the problem. It's the people west of us, west of Toronto, like in Vancouver or Alberta, who are even earlier, 3 hours earlier than Toronto. So 5 a.m. I think is an inappropriate time to write a test. So please fill out that survey, especially if you're in the category of west of Toronto. And I'm still trying to come up with an equitable, fair way for everybody involved. I don't want to give one group of students a disadvantage or, an advantage. I'm trying to make sure everything is equitable and fair for everyone. So please do that if you haven't already. All right, so without further ado, let's just move right on ahead. So hopefully you've looked at the pre-class for today. That should shed a lot of light onto what we're about to talk about. But I'm going to try what I did before with the last chapter with dynamics. I want to look at a set of questions ahead of time to help, two things, to help motivate why we're about to talk about what we're about to talk about, and two, give us a sort of benchmark. You can read these questions ahead of time and you can sort of get a sense of, I have no idea what the answers to these are now, which should make sense because we haven't done energy yet. And then after, when we're done energy, after Wednesday's lecture, hopefully we can go back after having taught all of the energy concepts. We can go back and then say, oh yeah, this is easy. And these questions aren't meant to be difficult by any means. They're pretty standard introductory level questions, but I kind of want to show your brain that you are in fact learning something with these lectures, even though it might feel confusing and you attempt new problems in the textbook and you might feel like you aren't getting anywhere, but you actually are, and it's just a matter of keeping with it. So that's what I'm trying to show you here is compare your knowledge before and after. So example, first question. The second floor of a house, let's say, is known to be 6 meters above the street level. How much work is required to lift a 300 kilogram fridge to the second story level, starting from obviously the street, because that's where it gets delivered? And if that alone isn't enough, there's another part to the question. Does the amount of work change if the fridge has to be carried up a staircase versus hoisted straight up, let's say with a pulley? Now, I can't imagine an average house would have a pulley in it, but let's say this is like an industrial building, and a lot of equipment gets moved in and out. Let's say there exists a pulley, that you can like hoist it straight up. Does the amount of work change if you have a pulley versus having to carry it up the stairs? Hopefully that question seems a little bit daunting at the moment, because it should. It's natural. We haven't talked about it yet. Second question we can look at. If we drop a banana off the top of a house, calculate the velocity before impact. That's fairly easy. In fact, we can do that as of the first lecture. That's just basic kinematics. The banana is in free fall. The initial speed in the y direction is 0. So a basic kinematics equation can solve for the final speed before impact. However, the follow-up to that, still free fall. If we drop a banana from space, let's say you take a hot air balloon up and it travels really, 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 really far. There will be a point at which the hot air balloon stops rising. Let's pretend that point is space. It will actually be fairly far out there. And you drop a banana from there. Calculate the speed right before impact. And of course, we're going to neglect air resistance. Are we able to also use kinematics for this problem? Maybe we are, maybe we're not. If we're not able to use kinematics, are you able to justify why? And a third question, which is one of my favorites actually. I think cars are the most interesting thing, not because I like them, like I'm not a mechanic or anything, just in terms of physics. There's a lot of physics that go on when you drive a car, and every time I get behind the wheel, I just see free body diagrams everywhere. you know, physics lenses. I don't wear glasses or contacts, but you know, I do wear physics glasses, which is kind of cool. So third question is, you're driving along the highway and you notice there's a traffic jam ahead of you. What should you do to maximize the chances of not crashing? Now, that question pretty much says if you're going too fast, you're going to crash regardless of what you try. But the question implies that there's a course of action that maximizes your chances of not crashing. And it gives you two options. Do you either, like here, for instance, for case one, do you try to turn your car in uniform circular motion away? So instead of traveling directly toward the traffic, you end up traveling perpendicular to traffic, and you just kind of drive off in the field. That's option number one. Or you do not turn at all. You just slam on your brakes, which is kind of what we've studied with kinematics. You know, it's just constant deceleration, traveling in a straight line. You know, we can study that using kinematics if we need to. We can also throw dynamics into there when we study friction, because you need dynamics to impact how friction, you know, quantifies or governs your acceleration or deceleration in this case. So that's the question. Do you turn to avoid a car crash, or do you try to stop linearly to avoid rear-ending somebody? So if you don't know how to answer that question at the moment, that's good, because you're not supposed to know how to answer that question. But these are sort of the things you can think about as we move through the upcoming lecture. And we can revisit this after Wednesday's lecture to see how much of it we can tackle. Okay, so to motivate this new chapter, I don't think I've mentioned it, we are going to start on energy this week. And I can't stress this enough. I've mentioned it a few times. Physicists, we don't study things just for the fun of it. I mean, we do find physics fun, so I suppose in that sense we study it because it's fun. But we do not just pioneer new physical theory just because we have nothing better to do. It's like, oh yeah, dynamics and kinematics wasn't hard enough. We need to add stuff to our workload. Like that's not even close to what we do in science, let alone physics. So if we are talking about energy, and every single university physics textbook will have an energy section in it, the natural question is, and as I've asked this question with the kinematics and dynamics as well, why? Why do we have a need? What piece of the puzzle are we missing? Why do we have a need for energy concepts anyway? I mean, I thought we were getting along just swimmingly without it. I mean, the story started with, you know, if motion exists, where is the item going to go? Where's the object going to go? That is kinematics, the study of trajectory. And then we said there was a glaring piece of the puzzle that was missing, is we assumed that motion already existed. We wanted to know what caused motion. And that's what gave birth to dynamics and forces and F naught equals ma and inertia and Newton's third law. And then we were happy. We said, oh yeah, we know what causes motion, and assuming motion exists, we know where it's going to go. And everything was hunky-dory, and it felt like we had the full picture. So why? Why do we need energy? I know we haven't talked about what energy is at the moment, but let's see if we can identify a piece of the puzzle that is missing, and then that'll help motivate the need for a whole other chapter to be developed. And a keen student might realize this. Now, I can 100% understand if what I'm about to say, you realize that in a million years you never would figure it out on your own. It's okay. Many physicists did not figure this out. You know, all it takes is one to figure out that there's a puzzle piece missing, and to let the scientific community know, and then everyone starts working on it. So you're not alone. But the piece of the puzzle that's missing is the fact that, and I introduced this right on the first day of lectures, we assumed the acceleration was constant. When we were looking at projectile or kinematics with projectile motion, for instance, we were looking at the fact that velocity was the integral of acceleration dt. And in order to proceed with any sort of analysis, we had to assume that the acceleration was constant. because if the acceleration was in fact constant, then the antiderivative of a constant is just a squared over 2 plus c. Oh, sorry, I'm sorry. A is a constant, so it's going to be at plus c. Sorry, and that was our only way to actually proceed with the integral. Now, in general, though, and I'm going to write this in red. In general, a doesn't have to be a constant. I mean, there's lots of things in life that don't have constant accelerations. I mean, even when you're driving your car, like the light is red, so you're stopped, and then when light is green, you know, you step on the gas pedal and you accelerate, and then once you've reached speed, you sort of ease up on the gas pedal. So you change how much acceleration you have. That's a non-constant acceleration, and that's just one example. I mean, there's literally almost anything in life has a non-constant acceleration. So there's a big gap to our story that we've been overlooking. And moreover, we carried this assumption into dynamics. When we studied F net equals ma, we always solved for, you know, acceleration, and we got a specific number. It wasn't a number as a function of time, it was just a number. The number was like 2 meters per second squared or something, right? That acceleration was also a constant. And to further imply kind of what the math implies here is the forces were constant. If you apply a constant force on an object, you're going to get a constant acceleration back. So really, question here is, what happens when you apply a non-constant force to an object? You're going to get a non-constant acceleration, which means non-constant acceleration means the kinematics equations we derived are no longer valid, which means there's a huge piece of the puzzle that is missing, and then that is literally the motivation for needing energy. Now, before we jump into the lecture, this is just a technical note. The last time in lecture we tried breakout sessions, it didn't go very well. Maybe it's because we were all kind of still new and didn't really know each other. Maybe we weren't really familiar with Zoom or something like that. But we've all had a tutorial last week, and in the tutorial you were encouraged in the breakout sessions to unmute yourselves and collaborate with other students with mixed success, I know. I would like to try it again. If it's a miserable failure a second time, I might have to revisit my idea, but please, we are going to try a breakout session at some point today. And I don't know how well it's going to go. Everything's an experiment in life. So we'll try it. Please, when I do put you guys into breakout rooms, please try to make an honest effort to unmute yourselves, chat, you know, maybe introduce yourself to the other people in your group, and you know, try to work on it. If someone is working on an iPad or like a computer that has a touch screen, you know, I encourage you to share your screen. You don't have to turn on your camera if you don't want to, but, you know, at least share your screen. And then that way everyone in your breakout session can at least see the questions, and you know, they can help tell you what to write and give you some ideas. Even if you're not on a tablet, you can still share your laptop screen. At least that way the group can see the question, and then you can verbally chat, you know, some ideas, some starting points, and, you know, you can grab some scrap paper on your own and start writing down solutions. You know, I just want to try it again just to see how it works, and you know, if it is an actual miserable failure, we'll figure this out for the future. But I just want to try it again today. Okay, so that's the prelude. Let's go right on to the lecture. So we are going to talk about work and energy, and I've already motivated the reason for needing energy, and it's to fill the gap of we do not always have a constant acceleration. And in the event that we do not have a constant acceleration, it is very difficult to analyze the specific trajectory the object goes, and it is very difficult to analyze you know, variables of motion like velocity, acceleration, and displacement. And thus dynamic approaches with forces also are difficult. So given the motivation, like I see the natural progression would be to start with something that's non-constant. However, before we jump into the juicy details, we have some legwork to do. We have some definitions to hammer out. We have some concepts to hammer out. And then once we have the legwork kind of under our belt, then we can jump to the juicy stuff. And I can show you kind of where all of this was birthed from. But unfortunately, before I start talking about joules of energy and you know, kinetic energy, we kind of need to know what those things are first before we jump into it. So let's start here. How did we relate kinematics and dynamics together? How did we relate trajectory analysis and forces analysis? And the way in which we did that was with the acceleration variable, and specifically the equation that related these two is F equals ma. A is a variable for motion, one of the many variables that motion includes, and force, F, or F net I should say, is a variable in the dynamics chapter. So F net equals ma is the coupling equation. It's the equation that marries the two chapters together. It provides you information from the dynamics unit, which is F net, and it provides information from the kinematics unit, which is A. So F net equals ma is the equation that relates those two chapters together. So similarly, we will need a similar concept in energy. We need something that marries or connects dynamics and energy together, forces and energy together. So that's what we're going to start with. That equation is called work done. Work done is measured in joules, so the unit there is joule. Please note that work done is a scalar, not a vector. It's a scalar quantity, and it quantifies how much energy a particular force puts in or takes out of a system. So the equation that, well, the specific equation by which it does this is this. Work equals F vector dot product with displacement vector. And if you forget grade 12 calculus and vectors, a dot product is a way in which we can combine two vectors. There's two different ways to multiply vectors. There's the dot product and the cross product. So we're going to take advantage of the dot product at the moment. And just as a reminder, dot product if you have two vectors, let's call this vector F, and let's call this vector D just for fun. Then the dot product is going to be, when we decompose vector F, let's call this F perpendicular, and there's another component of F here. Let's call this F parallel. If you decompose the force vector, or the first vector, into the two components, a component that's parallel to the displacement or parallel to the second vector, and a component that's perpendicular to the first vector, you'll notice here that the cos theta says F cos theta is in fact the parallel component, right? This is, let me just change the color so we don't get confused. This is the adjacent side where my green arrow is pointing, and cosine is the adjacent side. So F cos theta is actually the parallel component of the force in the direction of the displacement. So what is work actually calculating? We can see from the equation and we can see from the math that work takes the parallel component of force in the direction of displacement. So that means if you push straight upwards, and if for some reason the object goes forwards, maybe there's another force acting on it, maybe it had some inertia previously, and you know, inertia will carry it forward. Let's say if you push up, but the thing is still moving forward, you're doing no work on the object because your force is perpendicular, theta equals 90, to the displacement. So F dot D mathematically is FD cos theta. Cos of 90 is 0. So that's what work is doing. And the way in which you can think of this equation, as I mentioned before, is the equation that couples the two chapters together. It's the equation that relates dynamics, forces, with energy, in this case work, in the same way that F net equals ma relates kinematics and dynamics together. Okay, so we do know work takes in two vectors and spits out a scalar. So let's see if we can do an example now, just a very simple numerical example. It's by no means complicated. It's just meant to show you a simple situation in which the equation is used. So example 1 from the typed notes that are posted online, find the work done by a 45 Newton force pulling the suitcase at an angle of 50 degrees for a known distance of 75 meters. Presumably most of you have traveled before. You might have those sort of wheelie carry-on suitcases that you pull behind you. That's what this is describing. You're not pulling the suitcase, you're not crouched down pulling the suitcase horizontally, right? The applied force is not horizontal by any means. The applied force is coming from your arm and you're standing and walking normally. So your arm is kind of up on an angle. So there is a force involved. So it might be handy perhaps to draw a quasi-free body diagram. So this is your applied force from your hand. And we know it's at an angle of theta. And we also know the displacement is this way. Now, I didn't draw displacement on the free body diagram because displacement is not a force, right? It's a vector, yes, but displacement is not a force. So I did not attach it right on the free body diagram. All right, so now that we kind of have an idea of what's going on, we say work equals FD cos theta, and we're pulling the suitcase with 45 newtons of force across a distance of 75 meters. And the angle between the displacement vector and the force vector is 50. And that's as simple as it gets. We just go through here and we you know, can use a calculator if you want. We can calculate this. Now, if you did use a calculator, I think you should get 2170 joules.
Hey, Mark.
Yes, Brandon.
It seems that no one can see your writing and it's a bit frozen, the video, but the audio seems fine in the chat.
Interesting. I do not know. Technical issues are going to plague us for the whole semester. I know. Okay, let's see here. Hey, Brandon, can you, if I pause, is the writing updated in the window yet?
The last thing you finished writing was the joules, correct?
Yeah, it was 2170 joules.
Yeah, I can see that.
Okay.
But Crystal from the chat says she can't see it in real time and it just shows up as chunks every couple of seconds.
Interesting.
And another says everything is frozen.
Interesting. Okay, so it might be my Wi-Fi. What might be best at the moment is maybe we just take a little bit of a pause with the recording and maybe, I don't know, maybe have to find a different spot in my house. I don't know. Wi-Fi issues for the win. Okay, what I'm going to do now is I'm going to just stop the recording. If you're watching on YouTube later, I apologize for the technical difficulties, but you know, they're bound to happen eventually. I'm just going to take a pause and maybe find a different spot in maybe closer to the router, and maybe that makes a difference. I'll see you all in a few minutes.
Okay, we're back. Let's hope things are a little bit more stable this time. We've lost a little bit of time, so we're just gonna have to go a little bit quicker. So I'm not gonna launch a poll. We're just gonna talk about this. So here's like a true/false question, or a yes/no question. To work or not to work, is it possible to do work on an object that remains at rest? Well, if you look at the equation, work equals FD cos theta. If it remains at rest, is there a variable in FD cos theta that is affected by a zero velocity? And the answer is yes. You can push on objects that remain at rest. So force F could be anything. Theta, again, you can push on an angle, you can push straight on. Theta can be anything. But displacement, if the object remains at rest, then the displacement of the object is known to be zero. So here, the key word is here, if it remains at rest, what you're doing is you're doing F times 0 times cos theta, which you know you're going to get an answer of 0. So is it possible to do work on an object that remains at rest? No, it's not. And if I go to the next slide here, that's exactly what that summarizes for you there. Another multiple choice question. Again, because of time, we're not going to launch a poll. We're just going to go, I'll just dictate it because apparently the audio seems to be strong even in the times that the image is laggy. So a box is being pulled across a rough floor, rough meaning friction, known to be at a constant speed. What can you say about the work done by friction? Well, if you look at the equation, force equals FD cos theta. In this case, what force are we talking about? We're talking about the force of friction. So, you know, it might be helpful to draw a free body diagram. So if the box is, say, being pulled to the right, so picture a dot. If the picture is freezing, but the audio is okay, picture a free body diagram, picture a dot, and picture the displacement going to the right. But on the free body diagram, you have a resistive force of friction pointing to the left, force of friction backwards. So what's the angle between the force of friction, which is pointing to the left, and the displacement, which is to the right? So in this case, the theta value would be 180 degrees or pi radians, whichever you're more comfortable with. So it would be force of friction times displacement times cos of 180, and that's just going to be a negative value. Now, of course, how negative is a function of how far you pull it and, you know, how hard you pull it with and stuff like that. But you know it's going to be negative. So in terms of A, B, C, or D, friction does no work. Well, that's wrong. Friction does negative work. We know that's going to be correct. And friction does positive work. We know that's wrong. So the answer is going to be B. So there you go. There's B. Okay, another question. Again, for time's sake, we're not going to launch the poll. We're just going to do it. In a baseball game, the catcher stops a 90-mile-per-hour pitch. So that means the ball is thrown at the catcher. They hold out their baseball mitt, and the ball strikes their baseball mitt. And when it strikes their baseball mitt, it is traveling at 90 miles per hour. And then obviously the whole point of a catcher in a baseball mitt is it stops the ball. You know, you catch the ball and it brings the ball to rest in your hand. So what can you say about the work done by the catcher on the ball? So again, free body diagram, picture the ball. And what are the forces acting on the ball? Well, you've got a mitt that is applying a force backwards, let's say to the left, while the displacement of the ball is to the right. You know, it's toward the catcher. So again, we're in the same sort of boat where friction was when you were dragging a box across the ground. Although in this case, when you're doing a work equals FD cos theta, the force is not the force of friction, it's the force of the catcher on the ball, or force from the mitt on the ball. So it's not necessarily force of friction, it's just kind of like an arbitrary applied force, FA times displacement times cos of 180, which is going to be known to be a negative value as well. So the answer is B. Okay, here is example 2 from the typed notes. And there's no new information here. It's just an interesting consequence, I should say, of the math and the equations. And as with physics, it's always true in physics that the math has a meaning. And usually in undergraduate physics, the math is fairly straightforward, but the physical meaning is kind of lost in translation. So we're going to spend a lot of time talking about FD cos theta because there's a lot of fun little implications that this has. So for instance, we just finished talking about circular motion in the previous chapter. So, let's kind of see how energy, ties into circular motion. We did an example when we did orbits and gravitation that if you have an orbiting satellite, the satellite could be man-made, like, a Rogers or Bell or Telus satellite, or it could be a celestial satellite like the moon or another planet or an asteroid or something. So if you consider a moon, our moon, in uniform circular motion around the Earth, we know there's only one force acting on that body. It's gravity. So the free body diagram is actually given for you. And the green arrow there is velocity. So please don't confuse the green arrow as being a force. It's not. It's just indicating that the direction of motion at that moment in time, the instantaneous velocity, is tangential to the dotted line and directed, directly to the left. But overall, it's just going to follow the orbit here. So the question, though, is, does gravity do any sort of work on the moon? So again, we look at that equation, force of gravity, d cos theta. And the force of gravity is acting downwards. Displacement, well, for this very, 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 very instantaneous moment in time, the displacement is traveling in the direction of the speed, which is traveling directly left. So this is going to be force of gravity, displacement. And what's the angle between the left direction and the down direction? The angle between the velocity and the force of gravity is 90 degrees. I can see that from my diagram. And the cos of 90 is 0. So here we get 0 because it's not that the displacement is 0. The displacement is absolutely non-zero, right? The moon is moving. But the angle between the displacement and the force of gravity is 90. So there's actually no work being done on the moon. Now, I said earlier that work done is the equation that governs how much energy a force puts in or takes out of a system. So if the work done is 0 on the moon, then that means gravity, the force of gravity, does not take any energy out of the system and also does not put any energy into the system, which means the force of gravity, we know from the previous chapter, is responsible for maintaining the circular motion. So without the force of gravity, the moon would just wander away. But at the same time, the force of gravity does not change how much energy the moon has, meaning the moon will not get faster, nor will the moon get slower. So, orbits are this interesting mix, between a balance of forces that continue to be responsible for the circular motion, but at the same time, energy is not being added or taken out of the system. So it's this really nice sort of a perfect mix of variables that results in these sort of fun patterns that we're noticing. Okay, moving on, we're going to just try to look at some concepts from previous chapters, like dynamics, and kind of see how they relate to energy. So we also talked about pulleys and inclined planes, a topic that I would remind you is fair game for your midterm on Saturday. So, we're going to go from there and see how it connects to energy. So here's another one. A box is being pulled up a rough incline, rough meaning friction incline, by a rope, and it's connected to a pulley. How many forces are doing work on the box that are sitting on the incline? So again, the question is asking something about forces. So I would heed my advice from last week. Draw a free body diagram. You know, if forces are involved in any way, step one should always be drawing a free body diagram. And we know we're on a bit of a ramp, so let's draw a bit of a ramp there. Okay, so there's theta. And what are my forces? I'm going to change colors for forces here. So there's always gravity acting straight down. There is the normal force acting perpendicular to the ramp. There's tension directly up the ramp. And the little yellow arrows in the picture indicate that the block is traveling upwards, which means friction would be traveling backwards. And because we know the box is moving, it's kinetic friction, F of Fk, kinetic friction. So it looks like we've got 4 forces. Now the question is, how many of them do work? Well, in a different color here, we know work is Fd cos theta, just like before. So we actually have to look at the work equation 4 different times because we have 4 different forces. So let's take tension, for instance. Well, we're going to have work from tension equals the force of tension times the displacement times cos theta. Now, what's the angle between the direction of the tension force and the direction of motion? Tension is pointing up the ramp. Displacement is up the ramp. So the angle between them is 0, and cos of 0 is 1. So the work done due to tension is actually non-zero. So at least one force will do work. Let's pick another one. Let's say force of friction kinetic. Same thing, work equals force of friction kinetic times displacement times cos theta. Well, the displacement is up the ramp. Friction is down the ramp. So the angle between them is 180. So it's going to be negative. So non-zero and negative. So at least 2 forces will be doing work. Let's choose the normal force next, shall we? Work equals force normal times displacement times cos theta. And what's the angle between the normal force and the displacement? Well, the displacement is up the ramp, and the normal force is perpendicular to the ramp. So this actually means that the theta value is 90 degrees. And cos of 90 is 0, which means the work done to the normal force is 0. So far we only have 2 forces that actually do work. And the third force we have to analyze is the force of gravity. And saving a little bit of time without writing it out, you can see that the angle between the force of gravity and the displacement it's an obtuse angle. It's greater than 90 degrees. So it's going to be negative. The force of gravity does negative work because cos of an obtuse angle is negative. But it's non-zero is my point. It's going to be perhaps close to 0, but non-zero and negative. So 3 forces are going to be doing work on this object: the force of tension, the force of friction, and the force of gravity, 2 of which are negative, 1 of which is positive. The normal force will do no work. So if we scroll down here to the answer, that's exactly what we see here. Okay, so where does that leave us? We've done a lot of insights and then practice into kind of this new idea. We haven't delved terribly far into the new idea yet, but we introduced this notion that there was a hole in our analysis that we needed filling, and we came up with this idea of work. And work is the ability that a force has to either add energy or remove energy from a system. If work is positive, it's adding energy to the system. If work is negative, it's taking energy out of the system. However, we haven't really done the most obvious thing yet. F net equals ma is the net force on an object, and a being the resultant acceleration on an object. up until now, all the questions we've been doing is we've been looking at the amount of work an individual force has had on a system. So like, you know, the force of friction, specifically the work done due to friction, or the work done due to gravity, or the work done due to tension. But what about the network? Not like the network like internet or things like that, but like, you know, work subnet, the sum of all of the work done on the particular object. So the work done due to all of the forces on a specific object. So that's where we're going to go to from here. So let's start. I'm going to change to black. Let's start with Fnet equals ma. And if we remember in the back of our head that work in fact equals FD cos theta, please understand that mathematically what's actually happening is the dot product there. The cos theta is mostly inconsequential. So what happens here is if we take the dot product with displacement on the left side as well as the right side, because it's an equation, as long as we perform the same operation on the left as we do on the right side, you know, we're allowed to do it. So if we take the dot product on the left side and take the dot product on the right side with displacement, then this is the equation we get. And I'm going to switch back to black for a second. Here we go. So we know that F times D is work. Now this isn't any old F, it's specifically the net force. So the left side of this equation ends up being work net equals MAD. Now I'm going to drop the vectors for a second. Please understand that there is a general case of this is when you would add a cos theta. So it would be like AD cos theta, but you know, we're just going to leave that off for a second. Just because in the real sense, you could use calculus and you'd get the same answer as what we're about to get anyway. So I'm not going to confuse you. So we'll just say it's MAD. So W equals MAD, or W net equals MAD, or network equals MAD. And at the moment, I was mad at my network because it caused the screen to glitch earlier. Bad physics joke. Okay, anyway. So we have this AD, this A times displacement. So I think to myself, okay, is there an equation that I know that I can swap out A and D with? And you might remember we have this notion of V2 squared equals V1 squared plus 2AD. That's one of our kinematics equations. So if we solve for AD, we're going to get V2 squared minus V1 squared all over 2. And I can actually use this and swap it out in there. So this is going to be M times V2 squared minus V1 squared all over 2. And this is going to be 1/2 M V2 squared minus 1/2 M V1 squared. And this is actually a beautiful result. Although we haven't coined what this value is at the moment, we're about to. Even without a word for it, you can see that we pretty much have a subtraction of values. You know, we have whatever this represents. I'm going to change my color for a second. Whatever this quantity represents, which it is the kinetic energy. I haven't officially introduced that notion yet, but whatever this quantity represents, you can see that it's the final quantity minus the initial quantity. And we know that there's joules on the left-hand side. So each term on the right-hand side must have a unit of J, joules. So this tells me whatever this is, it's some sort of energy. And we have E2 minus E1. So in some sense, we know that it's going to be the change in energy. Now the question is, what kind of energy is this? And physicists were kind of stumbling into this analysis, and you know, you formalize things as you need to. So physicists got to this point and said, well, I have this quantity. It's not named yet. 1/2 M V2 squared, and then we're subtracting at 1/2 M V1 squared. So we're saying, you know, it's the final energy minus the initial energy, but what kind of energy is it? And physicists noticed that they have, m is inconsequential, really, m is just m, but v, they said, the bigger the speed is, the more energy this object has, and subsequently, the slower the object is, the less energy this object has. So, kinematics is a study of motion, and this type of energy is only dependent on motion. So naturally, the thing to label it is the kinetic energy, because it relates specifically to motion. So therefore, you get that the total amount of energy that a system receives or loses, the total, not individual components of, but the total amount of energy that the system as a whole receives can actually be calculated by looking at the change in the kinetic energy of the entire system. And an analogy to that would be like when you get paid, you might get, if you have a part-time job, you might get paid bi-weekly, you might get paid monthly, but throughout the month you're spending money, whether it be on rent or food or chips or Amazon Prime or ordering things on Amazon or what have you, right? So you have multiple contributions that, increase the energy of your bank account, you get paid. And you also have multiple things throughout the month that reduce the energy or take energy out of your bank account, like you spend money. So if you want to know what the net amount of money in your bank account is, you would simply just look at how much money you have at the end of the month and you compare it with how much money you have at the beginning of the month. And that's effectively what we're saying here, is if you want to know by what amount of energy your system changed by, all you have to do is look at the final amount of kinetic energy and subtract the initial amount of kinetic energy. And that's the total work done. So as we did before, let's see how this equation is useful. We're presenting a new equation. Again, not for no reason. There must be a reason for it. So let's look at this equation. So the work needed to stop a car. So for instance, I've mentioned this before. I love driving. Every time I get in a car, all I see is physics. Every aspect of a car, quite frankly, just screams physics. It is probably one of the most physicsy things that people use on a day-to-day basis. So I do a lot of car examples. So in driver's ed, they teach students that doubling your speed quadruples your distance, your stopping distance. But in driver's ed, I mean, how old are you in driver's ed? 16, 17, 18 years old. If you're before grade 12, you wouldn't have even had a chance to take physics. And even if you are of that age, there's no guarantee you've taken grade 12 physics. In fact, most people have not taken grade 12 physics. So driver's ed neglects to explain this statement. But I guarantee you that when you do take a driver's ed class, at least in Ontario, they do mention the phrase, if you're speeding, let's say there's a speed limit sign posted 50 kilometers per hour in a neighborhood, and for some reason you're doing 100 kilometers per hour. The reason why the speed limit's so slow is presumably if it's in a neighborhood, a child might step out in front of your car and you have to like slam on the brakes to not kill the child. So the reason why the speed limit's 50 kilometers per hour is the physicists that work for the city, they've deemed that, if your car is traveling at 50 kilometers per hour and you slam on your brakes, you can analyze the physics and the amount of distance required to stop the car is small enough that they feel drivers can safely react to children running in front of the car. And driver's ed says, well, if you double your speed, you actually quadruple the amount of distance required to bring that car to a stop. So let's say you used to take 1 meter to stop your car. Well, if you're traveling twice as fast, you actually will need 4 meters to stop your car. And 4 meters versus 1 meter may not seem like a lot, but if a young child runs in front of your car, you don't have a lot of time to react. So like every meter counts. So let's see if we can explain what driver's ed says. Let's see if we can use physics to back up the claim that if you double your speed, you quadruple the stopping distance. So if you draw a free body diagram of your car, let's say the car is in the middle of moving forwards, let's say, for instance. And if you slam on your brakes, then the only force responsible for stopping your car is friction. It's the only thing in contact with the road is your tires. So friction is acting backwards. So we can say that the net work done is going to be the work done by the net force times the stopping distance, the displacement of the car. And this is going to be the change in kinetic energy. And this equal sign is due to the work energy theorem. All right, well, presumably, let me just finish writing this. Okay, presumably, the whole point of this is to come to a stop. So your final velocity, in theory, should be 0, because that's what we're kind of aiming for here. So the right-hand side is just minus 1/2 mv1 squared, v1 being your initial speed. And the right-hand side is going to be the force of friction times the stopping distance. Sorry, cos theta. Cos theta. All right, now, the friction is backwards and the displacement is forwards. So cos theta is going to be -1 because theta is 180 degrees. Cos of 180 is -1. And this is a horizontal surface. So the force of friction is simply going to be mu mg times the stopping distance with a negative out front equals 1/2 mv1 squared. We see here that mass cancels. And what do we ask for? We're trying to relate the speed to the stopping distance. So I guess, I don't know, let's just solve for the stopping distance. It's going to be v squared over, oh, I forgot the negative here. And then that negative and this negative will cancel. Okay, there we go. V squared over 2 mu g. All right, so here is our final equation. And we see that the distance required to stop the car is equal to your initial speed squared divided by 2 mu g. So it's actually not a function of mass, whether you're driving a pickup truck, a smart car, or a regular sedan. You need the same amount of stopping distance as a function of your initial speed, which I find quite physically interesting. A lot of people would think, oh, I'm driving a very small car. I can stop faster than you. You're driving a big truck. That's not true. It takes the exact same amount of distance to stop. So what does this mean in terms of verifying the driver's ed program that you may or may not have taken? They said that if you double your speed, you quadruple your stopping distance. Well, you see here that the stopping distance is a function of v squared on the numerator, which means if you start with double your initial speed, then 2 squared is in fact going to be 4. So if you haven't seen this sort of analysis done before, let me show you here. I'll say, the stopping distance of, say, scenario 2 is going to be twice the initial, twice the old speed. So let's say v2 is equal to 2v1. So I guess I'll do this in steps for you. I'll say v2 squared over 2 mu g. And we know the speed in scenario 2 is actually 2 times the initial, the speed in scenario 1. So 2 times the speed in scenario 1 over 2 mu g. And bed mass, expanding the brackets here, we're going to get 4v squared over 2 mu g, which equals 4 times v squared over 2 mu. Oh, sorry, this is getting kind of 2 mu g. And this quantity by itself here is the stopping distance in scenario 1. So that means the stopping distance if you were to double your initial speed, d2, the stopping distance if you were to double your initial speed, is going to be 4 times the stopping distance if you did not double your initial speed. So that's using physics to sort of, verify what they're saying in driver's ed. Okay, moving right along. Gotta add more space. I don't know why this didn't move down. Okay, moving right along. Another question. A father racing his son has half the amount of kinetic energy of the son, who also has half of the mass of the father. So that sentence alone has a lot of words in it. So let's say, let the speed, I'm going to change to black. Let's say, let the speed of the father equal half of the speed of the son. And let's say the mass of the father is twice the mass of the son. The father speeds up by 1 meter per second and then has the same kinetic energy as the son. So V father after is going to be V father from before plus 1. So he speeds up by this much. And then has the same kinetic energy as the son. What are the original speeds of the father and the son? All right, so again, we just stick to basics. We know they're telling us that the kinetic energy of the father is equal to the kinetic energy of the son after he sped up by 1 meter per second. So the kinetic energy of the father is 1/2 mass father times V father plus 1 squared. And the kinetic energy of the son is 1/2 mass of the sun, V of the sun squared. And I think we just go through and calculate our numbers here. So simply, the 1/2s can cancel. That's easy enough to do. Mass of the father is going to be 2 times the mass of the sun. So this I can swap out. V father is half of the velocity of the sun. So that I can swap out. And at this point, the physics is all done. Now we just have to just go through and do some algebra. So draw. Let's cancel the mass of the sun. And I think what's next is bed mass. We have to expand the brackets. So 2 times 1/4 Vs squared plus Vs plus 1 equals Vs squared. Or actually, well, we could do this if you want. Another way is we could just take the square root of both sides. So, we could continue. Absolutely, that would also work. I'm just realizing now that we could just take the square root of both sides. The square root of 2 times 1/2 Vs plus 1 equals Vs. And now we simplify. So this is going to be what? Root 2/2 times Vs plus root 2 equals Vs. I need to insert more space. I wish there was a faster way to do that. All right, and now we just go nuts. Did I miss a minus sign somewhere? I don't know. This is turning out to be a negative. There's a negative velocity here. Oh, no, I'm not. No, it's not. It's fine. So this is 1 over root 2 Vs plus root 2 equals Vs. So root 2 is going to be 1 minus 1 over root 2 Vs, V sun. So the velocity of the sun is going to be root 2 over 1 minus 1 over root 2. And assuming you have Vs, you can go back and you can calculate the other one as needed. So according to my calculations ahead of time, I think this works out to be about 4.8 meters per second. And that implies that the velocity of the father is in fact going to be 2.4 meters per second. Okay, I'm hoping I didn't make a transcription error or calculation error there. But anyway, that's the gist of it. You're just kind of, the physics was done quite early on, and you're just sort of going through the motions and doing some algebra, some simple algebra there. Okay, now we have, again, inserting space is more convoluted than I want it to be. Okay, we've got one more problem. It's relatively simple before I have you guys try. Okay, so figure 4, which is from the typed notes here, but I'm including figure 4 right here for you. Figure 4 shows an overhead view of 3 horizontal forces acting on a cargo container or canister that was initially stationary, but now moves across a frictionless floor. Now, the whole point of that sentence is telling you, although there are 3 forces that are acting on this box, they're unbalanced, which means there's actually motion. Now, we're not telling you in that sentence where the motion is, we're just saying that the motion exists. The force magnitudes are 3 newtons, 4 newtons, and 10 newtons. And the 2 angles that are depicted in the question are 50 degrees and 35 degrees. And it's asking you for the net work done on the canister by the three forces during the first 4 meters of the displacement. So there's a lot to unpack there in that question. If you're getting kind of confused and lost, I would maybe just start working backwards here. It says that, what are they asking for? They're specifically asking for the net work that's done. So the net work that's done is F net times the displacement times cos theta. Now, if you think about it, the net work that's done it has to be parallel to the resulting displacement, because wherever the direction of the net force is going to be the same direction as the acceleration, and the acceleration is going to be parallel to the displacement vector. So we know ahead of time that theta is 0 and cos theta is going to be 1. We know that ahead of time. So really what we have to do is we have to figure out the magnitude of the net force, because we know the magnitude of the displacement is 4 meters. So that's already given to us in the question. A little bit of logic has figured out that we already have cos theta. Cos theta is 1 because theta is 0. So really this question, it's a really fancy way of asking students, what is the net force on the object? So it's a forces question, so we draw a free body diagram. Its free body diagram is pretty much already drawn for us. It's right here. And F1 is 3 newtons, F2 is 4 newtons, and F3 is 10 newtons, and this is 35 degrees, and this is 50 degrees. All right, so F net equals MA. So we're going to have F net in the x direction equals MA in the x direction. So just because we're doing energy now doesn't make my advice from last week any different. My advice from last week was, if you're doing a forces question, start with a free body diagram, then do F net equals MA. So that's what I'm doing. We're doing forces. I started with a free body diagram, then I moved on to F net equals MA. So what's my net force in the x direction? I've got a bunch of stuff going on here. So let's say, I don't know, let's let right be positive. So what's going on here? I've got one force pointing partially in the right direction. So it's going to be what? F3 cos theta 3. All right. I've got force 1 pointing backwards, minus F1. So F1's pointing left, so I make it negative. And I have part of F2 pointing backwards, so minus F2. And I'm going to draw the components of F2 in a different color for you. So I have F2 in the y direction and F2 in the x direction. So you can see here that F2 in the x direction is going to be opposite of angle theta 2. So that opposite is going to be sine theta 2. And this equals max. Now, in this question, I don't actually think we need the acceleration. So that's not necessarily, we don't need, we could solve for A if we needed to, but I don't think we need to. Going through here, F3 is 10. So this is going to be 10 times cos 35 minus 3 minus 4 times sine of, what's that angle, 50. And this is going to be F net in the x direction. And if you go through with this, I think you're going to end up getting 2.13 newtons. Now, how could I have approximated this without a calculator, for instance? Well, cos of 35 is really close to cos of 30, and cos of 30 is a special triangle. So cos of 30 is root 3 over 2. And sine of 50, again, I don't know what sine of 50 is without a calculator, but a theta value that's close to that we know is 45. It's only 5 degrees off, right? So sine of 45 is a special angle as well. Sine of 45 is 1 over root 2. So that could be one way you could approximate a solution without a calculator. But if you have a calculator, you can go ahead and do it. But I'm trying to show you why we started the class with measurement and estimation, right? These themes pop up kind of throughout the course. Anyway, so we have F net in the x direction. We can do the same thing in the y direction. F net in the y direction. F net in the y direction is going to be, let's see here, F3 sine theta 3. F1 is actually not pointing at all in any capacity in the x direction, or sorry, in the y direction. So F1 doesn't even pop into this at all. And we have F2. Part of F2 is pointing in the y direction. Specifically, it's pointing in the negative y direction. So it's going to be a negative theta 2. And if we plug in our values here, we're going to get 10 sine of 35 minus 4 cos of 50. And again, you may not have, like, if you don't have a calculator, you could approximate this. Sine of 35 is really close to the sine of 30. The sine of 30 is a half, so half of 10 is 5. and 4 times cos of 50. Cos of 50 is close to the cos of 45. Cos of 45 is 1 over root 2. So you're dividing 4 by 1 over, or dividing 4 by root 2. So it's like, you know, root 2 is what, 1.7321 or something like that. So almost 2. 4 over 2 is 2. So it's like 5 minus 2. Your answer should be around 3. Now, if you had a calculator, I think you're going to get 3.17. But if you had to approximate this, for instance, you could say that 10 times a half minus 4 over root 2. And this is also approximately equal to 4 over 2. Root 2 is not 2. I fully understand that. But it's, if you're doing, you know, approximating, you can approximate it to around 2. In fact, what is the square root of 2? Just to see here. Oh, sorry, it's 1.4. It's 1.4. So maybe putting it 2 is a little bit too over ambitious, but you know, we're approximating. So this is sort of close to 5 minus 2, which is in and around 3. So if you were approximating, let's say you're not having a good relationship with your calculator on the day of the midterm. It's a really long computation. You just want to make sure you're in the right area on the midterm. It's really good to just sort of do the sort of back of the envelope calculation to make sure you're not too far off. So if my calculator is telling me the answer is 3.17 and my sort of rough calculations are telling me the answer is 3, odds are my calculator and I have a good relationship, at least for the time being. We may not for the next question, but anyway. So the Fnet in the Fnet in the y direction is 3.17 newtons. So what does that make the overall net force? Well, the overall net force, rather I should say the magnitude of the overall net force, is going to be Fnet x squared plus Fnet y squared, right? Just the hypotenuse, the Pythagorean distance between the two of them. And this means it's going to be 2.13 squared plus 3.17 squared, all square rooted. And if you add those two together and you take the square root, I believe the answer is 3.82 newtons, which makes the net work FD, which makes the net work 3.82 times 4, which is going to be about 15.3 joules. So that's the net work done on this object that is being pulled in 3 different directions. All right, so this is where we're going to try a breakout session. I think we've recovered from the time loss that we had with the internet interruption earlier, because I skipped a bunch of the polling questions. So I think I've recovered enough time to maybe try a breakout session this time. I've got 2 breakout session questions lined up. We may not have time for both of them, I'm not sure, but I at least want to try one to see how well this is going to work. You've seen me for the past, I don't know, 40 minutes, maybe longer, 50 minutes, doing question after question after question. You've seen me use the work equation, work equals FD cos theta. You've seen me use the work energy theorem. I want to see if you guys can try to do this on your own without just kind of me spoon feeding you the answers, because it's really important for your brain to get involved and for your brain to, you know, actually try to set up a problem and work through it. If you're just passively listening to me do the questions, I don't know, sometimes things don't connect all the time. So please be prepared. As I mentioned before, please give an honest effort to these breakout sessions. If you happen to have a tablet, like either an iPad or just a computer that has a touch screen on it, please make an effort to screen share these PDFs, because then that way all of your group mates can see the question all at once. And even if no one in your breakout session has a touch screen, like that's okay. Just one of you, I encourage you to please share your computer screen, and then that way it's displayed for everybody, and then you can chat about it. You know, please unmute your microphones. You know, You know, I know some of you are shy. I understand that, but you know, please try to make an honest effort here. For those of you watching on YouTube, I'm going to stop the recording now, just because when there's a breakout session, you're not going to see anything because we're all going to be in separate rooms. So if you're on YouTube, please join us for the solution to this later. Well, for you it'll just be a few seconds, but for us it'll be much later. So once I break you out into the breakout sessions, Brandon and I will jump around to the different breakout sessions, and we'll see how you guys are kind of spinning things up to make sure, you know, you guys are unmuting yourself and talking and sharing your screen and working on the problem. And, you know, we're also here to kind of help you with technical difficulties. Hopefully there aren't any, but, you know, we'll see. Okay, I'm going to stop the recording now for those of you on YouTube. I'll see you guys momentarily. Okay, welcome back everyone. If you're joining us on YouTube, it'll just feel like a moment later for you. So we've had, I don't know, about 20 minutes to work on this problem. From what I can see, the breakout sessions were slightly more successful this time compared to last time. So, you know, maybe it's just a comfort level for some students, unmuting yourselves and chatting. Maybe some technical issues were happening as well. So we'll see. Maybe we'll try this again tomorrow and reevaluate. But before we end the lecture, I think it would be nice to sort of have a solution to compare against. Now that most of your brains have had a chance to sort of read the question, set it up on your own without me holding your hand and immediately spoon feeding the answer, maybe now when I present the solution, things will make a little bit more sense. So let's just have at it. So suppose a probe, let's say in space, I guess from the picture, has a known mass of 747 kilograms. So I see a number. Let's just write that down. Mass equals 407. Oh, I even said that number wrong. 474 kilograms. Is traveling with an initial speed of 275 meters per second, initial speed. No force acts on it except the very small amount of thrusters that it has. So it has 5.6 times 10 to the minus 2 newtons of thrust. That's a very, very, very small amount of thrust. This external force is directed parallel to the displacement of 2.42 times 10 to the 9 meters. Wow, such a small force caused a distance to be, you know, quite a large distance. Determine the final speed of the probe, assuming the mass remains nearly constant. So first of all, we can understand sort of the context here. We are in space, so there is no friction. And so even a small amount of force, I mean, like if you look at the F net equals ma equation, if the net force, even if the net force is small, if like, you know, if the net force is 5.6 times 10 to the minus 2 newtons, that would still mean that there is a non-zero acceleration. And if there's no friction, there's no air resistance, you know, a small amount of force and a small amount of acceleration will eventually make this item, you know, travel something substantially far, and if left to accelerate long enough, the final speed will be something substantial as well. So that's the whole nature of space physics. Space physics is actually remarkably easier than earthly physics, because earthly physics we have to make a bunch of approximations. You know, there's friction, there's drag, there's air resistance, and all this other stuff. In space, none of that's a problem. So doing space physics is actually quite a bit easier than Earth physics. Anyway, that's just for context. Let's actually do the question here. So we want to know the final speed of the object. So I'm trying to relate and trying to get my head wrapped around this. So we're trying to relate force, displacement, velocity, and mass. And we could, in fact, do this using F net equals ma coupled with kinematics equations. We could find the acceleration using F net equals ma. And we know the displacement, we know the initial speed. So, you know, we could actually just use v2 squared equals v1 squared plus 2ad. And we can get a from F net equals ma. So if we wanted to, we could absolutely just do that. And we can do that in this case because it's a constant force, so we're not violating any rules for our kinematics equations because it is a constant acceleration. However, let's see if we can practice doing it another way. So I know that from the work energy theorem, the net work that's done is going to be the net force times displacement. Now, in general, yes, there's a cosine theta there. However, the net force will always be in the same direction as the displacement. And I explained that earlier, right? The net force has the same direction as vector as the acceleration. The acceleration is either going to be parallel or anti-parallel to the displacement. But if it's a net acceleration, it's cos theta is going to be theta is going to be 0, so cos theta is going to be 1. So this is your the net work done is F net dot d. And we know from the work energy theorem, this is going to be the change in the kinetic energy. So that's going to be 1/2 m v2 squared minus 1/2 m v1 squared. So we're asked for v2. We have m, we have v1, we have the displacement. And with a free body diagram, you'll realize the only force that goes into F net is the force of the thrusters. So if we were to draw, a free body diagram here, you see that the only force is the force forward of the thrusters. Right there. And so we do have the net force. The net force is in fact just the force F from the question. So we have everything except V2. So we can actually just go ahead and solve for V2 here. So we're going to have the force of the thrusters times the displacement is going to equal to, let's bring over plus 1/2 m v1 squared equals 1/2 m v2 squared. We're solving for V2. So let's bring up this. So 2fd plus mv1 squared equals mv2 squared. And insert some space. There we go. And we're solving for V2. So one more rearrangement. Square root. This is going to be 2fd over m plus v1 squared, all square rooted, is going to be your final velocity. And this actually works out to be the same answer if we did it using a combination of dynamics and kinematics. So if you want to sort of see a second way to analyze this, I'll say because of constant acceleration, we can use, oh boy, what happened there? We can use kinematics and dynamics. So we can say the net force is F equals ma, which means the acceleration is F over m. And we can say v2 squared equals v1 squared plus 2ad, and the acceleration is F over m, which means v2 is going to equal the square root of v1 squared plus 2fd over m, which is the same equation that we derived previously using energy concepts. So this just shows you that even though we've introduced a new idea, energy, work, and the work energy theorem, they're not independent from one another. They're definitely related. And our assumption for the previous types of analysis with dynamics and kinematics being acceleration is constant. If acceleration is constant, then I guess the moral of the story is it doesn't really matter how you approach the analysis. If you want to use energy concepts, go nuts. If you want to use a combination of dynamics and kinematics, go nuts, right? Our need for energy did not come from the fact that we couldn't analyze things before that had constant acceleration. If it had constant acceleration, we could do it. That wasn't an issue. The issue is when we did not have constant acceleration. And so, you know, we will do it tomorrow, but we have yet to see an example when we do not have constant acceleration. So I guess the takeaway is, yes, it's something new. We've put in a lot of legwork now into developing these new ideas. However, all the situations I've presented with you today have constant acceleration, because I didn't want to change too many things at a time for you guys. I wanted to just reintroduce or to introduce one very simple new concept and have that new concept applied to things previous that you're already familiar with. So things with constant acceleration you guys are familiar with. So hopefully it helps your brains kind of put into perspective this new piece of information. And then tomorrow we're going to add a layer where acceleration is not constant and really show you the power of energy and why energy is so useful as an analysis technique. Okay, so if you're watching us on YouTube, thanks for sticking to the end. This is the end of the material for today, so I'm going to stop the recording shortly, and I'll see you tomorrow. And after I stop the recording, I'll take some questions from the chat window. All right, I will see everyone tomorrow.